Acceleration is another vector you will commonly come across in physics. A vector, by way of review, is a quantity that includes both the magnitude and direction. Acceleration is defined as the change in velocity of an object over time, or also the change in speed of the object over time. Let's say we have a mass initially at rest, so its initial speed or velocity is 0 meters per second, and as it accelerates, its speed will increase over time to a final velocity or speed of 10 meters per second. We can better analyze the change in velocity of this mass on a velocity versus time graph, where the y-axis is the object's velocity and x-axis is the time. If an object has a uniform or constant acceleration, the velocity increases over time in a linear manner. In other words, the relationship between velocity and time is represented by a straight line of best fit. Here, we can see that the object increases its velocity from 0 meters per second to 10 meters per second over the span of 2 seconds. So we can calculate the acceleration by taking the final velocity minus the initial velocity, which gives you the change in velocity, divided by the change in time. That's called the delta t. This is equal to 10 meters per second minus 0 divided by 2 seconds. And we'll get a magnitude of acceleration of 5 meters per second squared. This means that the object increases its velocity or speed by 5 meters per second every second. And that's why in a span of 2 seconds, it reaches a final speed or velocity of 10 meters per second. When an object has uniform acceleration, its velocity versus time graph is represented by a straight line. If we graph the acceleration versus time, we can see that this is represented by a horizontal line, as the acceleration magnitude is constant. And as we previously calculated, the acceleration of the object was 5 meters per second squared. And this is why the horizontal line is at 5 meters per second squared on the y-axis. Another important relationship you should understand between the velocity versus time graph and the acceleration versus time graph is that the gradient of the straight line in the velocity versus time graph represents the acceleration. So when we calculate the gradient of this straight line, this is equal to the acceleration of the object. This should make sense to you because gradient is defined as the rise of the object divided by the run of the object. The rise of the object is the change in velocity, and the run of the straight line represents the change in time. So the gradient in this scenario is the rise of the object, which is the change in velocity, v minus u, where u is the initial velocity, divided by the run, which is the change in time. And as we saw previously, this is equal to the acceleration. So when you get a velocity versus time graph, the gradient of the straight line is equal to the acceleration of the object. And since objects that undergo uniform acceleration have a constant acceleration, the gradient of the velocity versus time graph always has a constant gradient. In other words, they are always a straight line. It is possible for an object to have a negative velocity while having a positive acceleration. Negative velocity means that the object is moving in a negative direction. Remember, velocity is a vector quantity, so you must include a direction. Positive acceleration means that the acceleration is towards the positive direction. So in this case, the direction of the acceleration is the opposite to that of the velocity. Whenever the direction of the acceleration is opposite to the direction of velocity, the speed, that is the magnitude of velocity, decreases. So in this case, the object's initial velocity was minus 10 meters per second, and over time, due to the positive acceleration, the velocity becomes less negative and reaches a speed of 0 meters per second after 2 seconds. Here, we can also use a gradient of the straight line to calculate the acceleration. So acceleration is equal to v minus u divided by the change in time. The final velocity is 0 meters per second minus the initial velocity, which is minus 10 meters per second, divided by 2 seconds, and this will give us 5 meters per second squared. And this is shown by the same horizontal line in my acceleration versus time graph. It is possible for an object to have a negative acceleration as well. When an object has a negative acceleration, the velocity always decreases. For example, let's say you have an object that has an initial velocity of 10 meters per second, and it has an acceleration at -5 meters per second squared. This means every second, the object's velocity will decrease by 5 meters per second. So after 1 second, it will decrease from 10 meters per second to 5 meters per second. And after 2 seconds, it will decrease to 0 meters per second. And again, we can calculate the gradient of the velocity versus time graph to confirm that the acceleration is indeed -5 meters per second squared. So here, the gradient is equal to the final velocity, which is 0, minus the initial velocity, which is 10 meters per second, divided by the span of 2 seconds, and we'll get -5 meters per second squared. When an object has a negative acceleration with a positive velocity, this is also known as deceleration, because the negative acceleration will decrease the speed of the object. Okay, so what happens if an object's velocity and acceleration are both negative? Well, remember, negative acceleration always decreases an object's velocity. So if an object already has a negative velocity to start with, its velocity will become more and more negative as it further decreases. So here, the object starts at rest with a velocity of 0 meters per second. After 1 second, it will reach a negative velocity of -5 meters per second. And after 2 seconds, it will reach a velocity of -10 meters per second. So the gradient of the straight line is the final velocity, which is -10 meters per second, minus 0, which is the initial velocity, divided by 2 seconds. And this gives us -5 meters per second squared, as shown by the acceleration versus time graph. In this scenario, since the velocity and acceleration have the same direction, that is being both negative, the acceleration actually increases the speed of the object. So even though the velocity decreases and becomes more negative, the object actually travels faster over time because its speed, which is the magnitude of velocity, increases. So if you look at the y-axis, in the beginning, it travels at -2, which means the speed is 2 meters per second, -4, which means the speed is 4 meters per second. If you just focus on the numbers, ignoring the negative sign, you can see that the speed increases to 6, to 8, and finally 10 meters per second. The direction of an object's velocity and its acceleration determines whether its speed actually increases or decreases. An object will speed up if its acceleration and velocity are positive. In this case, the positive acceleration will cause the velocity to increase over time. It will cause it to become more and more positive as time passes by. An object will also speed up if its acceleration and velocity are both negative. This means the negative acceleration will cause the velocity to become more and more negative over time, but the speed of the object still increases over time. So when an object's acceleration and velocity are both in the same direction, you would expect its speed to increase. That is, in simple words, it will travel faster over time. Now, in contrast, if an object's acceleration is negative, while its velocity is positive, that is, if they're in the opposite direction, the object will slow down. Its speed will decrease over time. So in this instance, the velocity of the object will become less and less positive as time passes by. Similarly, if an object's acceleration is positive, but then its velocity is negative, it will also slow down over time. In this case, starting with a negative velocity, the velocity will increase over time, becoming less and less negative due to the positive acceleration. So if you focus on the magnitude of velocity, that is the speed, it goes from 10 to 8 to 6 to 4 to 2, and then eventually 0, meaning that it's traveling slower and slower over time. So when an object's acceleration and velocity are in the opposite direction, you would expect its speed to decrease over time. That is, it will travel slower and slower over time. It is also important to integrate how acceleration and velocity affects an object's displacement over time. And higher velocity means that an object travels a greater displacement over time. This is the definition of velocity, that is, the change in displacement over the change in time. When we're looking at the displacement versus time graphs, pay extra attention to the gradients because the gradient of these graphs represents the velocity of the object for that particular interval in time. And when an object has uniform acceleration, you will expect the displacement versus time graph to have a parabolic shape. So here we have the velocity versus time graph for an object with positive acceleration and positive velocity. So over the span of 2 seconds, its velocity becomes more and more positive. That means it's traveling faster and faster. If the object travels faster with time, you would expect it to travel a greater displacement over time as well. In the first 0.4 seconds, it only travels a small distance because its velocity is quite small. But then in the second 0.4 seconds, it travels a greater displacement. So you can see the vertical distance between the data points is becoming larger as we speak. As time passes by, a greater displacement is traveled by the object. When you see the trend represented by these data points, you can clearly see that this is a parabolic relationship. The slope or the gradient of this curve becomes larger and larger with time, and that's because the gradient of the displacement versus time graph represents the velocity. There are two kinematic equations you will come across commonly that involves displacement. The first one is displacement of the object is equal to its initial velocity, which is u, times by time, plus half times by the acceleration of the object. And here we are assuming that the object has a uniform or constant acceleration, times by t squared. The second equation is the final velocity of the object after the acceleration, that's v, so final velocity, equals to u squared. Again, u squared here is your initial velocity, plus 2as. A is the acceleration and s is the displacement during this acceleration. So now that we've looked at what the displacement versus time graph looks like when an object has positive acceleration, what happens if it's got a negative acceleration while having a positive velocity? Now we mentioned earlier, when your velocity is positive, but then your acceleration is negative, that is, if they're in the opposite direction, the speed of the object will decrease over time, meaning it will travel slower and slower over time. So here we can see that the velocity starts at 10 meters per second and decreases to 0 meters per second over 2 seconds. This means on the displacement versus time graph, you will expect the greatest displacement to be covered in the first 0.4 seconds, and in the second 0.4 seconds, a smaller displacement will be covered, and it will continue to decrease due to the decreasing speed of the object. And eventually, in the very final interval of the 2 seconds, the object travels the smallest displacement compared to the rest. When you're looking at the data points as a whole, it is still represented by a parabola. But in this case, the parabola has a largest gradient at the beginning, representing the greatest speed or velocity, and the gradient or slope decreases with time, meaning that the object is decelerating. It has a negative acceleration acting on its positive velocity. What about if the velocity of the object and the acceleration are both negative? That is, it's traveling in a negative direction with a negative acceleration. We mentioned earlier that if the velocity and the acceleration are in the same direction, so in this case the acceleration is negative, the velocity is also negative, the speed of the object will actually increase over time. So if you look at the velocity axis, the speed goes to 2, goes to 4, 6, 8, and 10 over time. So it goes faster and faster. So we'll expect the displacement of the object to be also negative to start with, because the object is traveling in a negative direction as indicated by its negative velocity. So in the first 0.4 seconds, it covers the smallest displacement possible, and then the displacement becomes more and more negative in the subsequent intervals. And in the final 0.4 seconds, it travels the greatest negative displacement compared to the other intervals. So these data points, again, is represented by an upside down parabola, as the displacement is now negative due to a negative velocity. This concludes the video on graphs of objects in motion with uniform acceleration.